I'm Chad Beamer with Quintus Technologies, and welcome to Tech Talks. Today we have a well-established and respected professor from Penn State University leading the way in processing, characterization, and testing of additively manufactured materials. Could you introduce yourself, discuss Penn State University and the facilities, as well as highlight your area of expertise?
Oh, well, thanks, Chad. My name is Todd Palmer. I'm a professor of engineering science and mechanics and material science and engineering at Penn State. I've been at Penn State as a professor since about 2017, since about 2007 in total, when I started at the Applied Research Lab. But my career really started at Lawrence Livermore National Labs in the early 2000s, and I really cut my teeth and really developed there as more of a welding and joining engineer. And so I did a lot of laser and electron beam processing of a wide range of materials. Some ways I think I probably welded or at least processed about everything that was on the periodic table, it felt at times. And so I was there for about 7 years, and then I moved to Penn State and I started at the Applied Research Laboratory. And so moving from Lawrence Livermore in one national security aspect into another one where I did a lot of support work through the Applied Research Lab for the Department of Defense. And a lot of that involved laser deposition. So I moved a little bit from welding and a little more into laser deposition. And over the years at ARL, that morphed much more into what is really looked at now as additive manufacturing. And so we took our laser cladding, our laser deposition experience, and applied that into the building of parts and really developed into where additive manufacturing is today. We played a big role on some of the early programs with DARPA at that time. And so Penn State has a fairly rich history in additive manufacturing. It actually goes back into the 90s and what I would consider sort of the first iteration of additive manufacturing, where they were really looking at free-form technologies, they were called at that point in time. And so Penn State has been building off that since then. And so now we have facilities, a wide range of professors working on different aspects of the additive process.
Quite the history, and explains why you have arrived in the AM space today. Quintus and Penn State University has been collaborating for some time now, over 5 years. Can you speak a little bit about the scope of our collaboration and the motivation behind some of the work we're involved in?
Oh, absolutely. And Quintus has been invaluable to my group. We've probably, I can say, between about 5 and 7 graduate students have benefited directly from working with Quintus and the opportunities that you've given us to really process a wide range of materials. And you really look at the material systems that we've been working on, they really go across a wide range of applications and properties, from titanium to nickel-based alloys, whether it was more common ones like Inconel 625 or 718, into duplex stainless steels, precipitation-hardened stainless steels, and you've even done some work for us in the austenitic stainless steel region. So we've really gone across the gamut, and really Quintus has been a key player in all of that, whether it was just the idea of hot isostatically pressing in order to have us test mechanical properties in that condition and to reduce process-related defects, or to actually start manipulating microstructures and having us really track that microstructural evolution.
Can you provide us a little more depth on some of the material systems you have recently evaluated, and how that's maybe steering or directing some of your future work?
So we really started, I think, where most everybody else did with Ti 6.4. And so really starting with that alloy system. And it grew out of programs that we had of really looking at accelerated certification. So if you look back even over the last, say, 10 years in the additive space, certification, qualification are the overriding factors or any starting point for any discussion. So we started in that area. And we were looking at Ti 6.4 primarily just to see what mechanical properties we could obtain. And being able to hot isostatically press those and to really see the importance of hot isostatic pressing in reducing uncertainty in mechanical properties. Whereas when we look at as deposited or as built properties in Ti 6.4, they are spread out all over the place. There are huge variations in the properties. And when you hot isostatically press them, those variations tend to get really a lot narrower. And it's much more of an attractive range of properties for designers than what the current as deposited materials are. So we started there, but what we really went beyond is we started really investigating what happens to the microstructures once you hot isostatically press them. And so we were looking at the evolution of different phases, how the microstructure coarsened or became refined under different heat treatments. And Quintus was an important player in that. We moved on from there into Inconel 625, a range of different duplex stainless steels, looking at not so much how the hot isostatic pressing process impacted the mechanical properties, but a little more in how they were impacting microstructural evolution and how we could maybe use the process to control the microstructures that we were forming. And so that worked our way in even into precipitation hardened stainless steels, which are a much more complex endeavor than some of the other materials. The other ones were complex, but the 17-4 grade, even though it's been around for about 50, 60 years, it is really presenting some challenges, especially in terms of compositional variations for us. So we're really, that's where a lot of my focus is heading in now.
And you're also starting to evaluate the workhorse alloy, right, of aviation space, Inconel 718, which is,
Yes.
is very complex in itself as well. Could you speak a little bit about what you're investigating there around HIP and the possibility of controlled cooling or rapid cooling in a HIP vessel?
So in 718, where we really are looking is a little less on the property side. I doubt even in a lot of the work that we're doing that we're probably even going to pull a tensile specimen. What we're really concentrating on is what are the roles of high temperature heat treatments in 718, because the alloy, even though when it's processed, it's going through all this range of thermomechanical processing to get it into the appropriate shapes. In order to obtain the properties, it has to be subjected to some rather controlled and rather complex heat treat cycles. Now, when you take something that's been additively manufactured, where you take basically a 718 powder and melt it with a laser, that microstructure looks a lot different, that starting microstructure. So it's something that we call really a highly segregated. So a lot of the important alloying elements are stuck in and around in different areas, and so they're segregated around. So you have almost like a composite type structure. And so how does that structure interact with the high temperature heat treatments is one area where we've started. And hot isostatic pressing is one way to obtain that type of solutionizing. It's what the heat treatment is typically called, as homogenization, solutionizing, and then aging heat treatments that they go through. Now, in terms of the alloy, what we found is that if you don't control the cooling rate coming out of the high temperature transformations, you actually start the aging process. And what that's going to do is limit the end state properties that you can obtain out of it. So being able to rapidly cool and to control that cooling rate coming out of the high temperature heat treatments that a lot of the Quintus systems offer is really something that is critical to developing an improved understanding of what we are really after in obtaining good or maybe even superior properties to the rot conditions.
And you touched base on it. Some of the advancements with HIP equipment and technology around it is enabling that to be performed today, not only in a lab HIP vessel, but it's also commercially available at a number of service providers. From the uniform rapid cooling that is controllable to uniform rapid quenching, which is possible to cool up to oil or polymeric type rates. We're really interested to continue to see the work that you develop and grow off of at Penn State University. Can you give us some teasers on what's to come from Penn State University?
Well, I think there's a little more, a couple areas that we are really interested in. And the first one is really the presence of interstitial alloying elements. And so I use that term more to think about alloying elements in that you don't really always measure or think about, and that's things like nitrogen and oxygen. And so I have a little bit more of a background. My PhD dissertation from over 20 years ago, approaching 25 here rapidly, really focused on the absorption or dissolution of nitrogen during arc welding of steels. And so nitrogen, as it's absorbed, can do some very interesting things. In austenitic stainless steels, it improves corrosion resistance. It can actually increase strength in some cases. In some of the pH grade stainlesses, what we're finding, especially during additive, is that it's impacting the heat treat response. And so being able to understand that is critical. Even in like Inconel 625, we're in the process of having a paper. It's sort of going through review now, but should be available shortly. Is that we actually saw that when you manipulate the nitrogen composition in the alloy, you actually really introduce phases that aren't typically seen in the alloy. So you actually take the thermodynamics of the alloy and sort of flip it around, and you produce some high temperature secondary phases that may have some good properties leading further on. We're investigating that. And so really getting into the idea of maybe looking at lower temperature, lower cost, higher temperature performing nickel-based alloys. Another area that we're really interested in is the role of oxide inclusions. And so since most of the time in additive we start with a powder, what we are really looking at is we can have upwards of an order of magnitude more oxygen in an as-built AM part than we would in a wrought component. Once again, that shifts that thermodynamics. So this idea of whether you're talking CalFad, whether you're talking ICME, whichever the appropriate buzzwords are for this week on the use of computations, it allows us to start looking at how they evolve. Because really, we started looking at duplex stainless steel powders, austenitic, really at the powders themselves, and taking them and putting them in a transmission electron microscope. We found that there are oxide particles in there, but they're spherical and they're amorphous, and that's just not on the surface. So the stock answer for most people is well, you're not handling your powder properly. You're picking up oxygen. Well, we're handling the powder properly, but we're actually cutting and cross-sectioning the powder particles and having them, for the most part, give us the ability to sort of see inside the particle, and we find these oxide inclusions there as well. And so moving on from that, we want to see how they evolve with hot isostatic pressing. And we found in some of our initial studies that they evolve into the crystalline structures that we have. Now, how does that impact properties is an area that we're really interested in. And what we're finding is that there are some impacts of these oxide inclusions. So we want to understand how to control them and actually how they're impacting the properties.
You're speaking a little bit around, right, design for AM considerations here, and
Yes.
and also more of a holistic view with AM to really optimize the material, continuing to build out the process, structure, property, relationship fundamentals that you've really focused on from day one. Speaking on behalf of Quintus Technologies, we want to thank you for the strong collaborations over the years, Todd, and I personally look forward to seeing what's to come. In ending, I want to thank you for your time, your insight in AM and developments with nickel-based alloys, as well as HIP and high-pressure heat treatment.
Well, we do appreciate, and as I said, I'd like to thank Quintus again for all the help and the support they've given us over the last several years. through various people, Magnus and Anders have also helped as you have, Chad, and really supporting our students and having them be able to really be exposed to this different range of technologies and have it support their research work.
Thank you.
Thank you.